The Quest for a Common Model of the Intelligent Decision Maker. By Richard Sutton, the first author of the Reinforcement Learning textbook. The common model of the intelligent agent, substantive and widely held across psychology, artificial intelligence, economics, control theory, and neuroscience. The common model does include aspects of the decision maker's interaction with its world. There must be input and output, and a goal, and internal components of the decision maker, for perception, decision making, internal evaluation, and a world model. The decision maker makes its decisions over time, which may be divided into discrete steps at each of which new information is received and a decision is made that may affect the information that is received later. In psychology, the decision maker is the organism, receiving stimuli and sending responses to its environment. In control theory, the decision maker is termed the controller, receiving state and sending control signals to the plant. A dictionary definition of agent: a person or thing that takes an active role or produces a specified effect. The term agent is also preferable to decision maker because it connotes autonomy and purposiveness. What then does the decision-making agent interact with? One answer is that it interacts with everything that is not the agent, which might be termed its environment or world. Let's go with world, because it is simpler and shorter while also being evocative in a way not linked to any specific discipline. The agent takes actions, and receives sensations or observations. Let us use observations because it is an established term for this purpose and avoids metaphysical discussions about whether a machine can have sensation. Observations means information about the state of the world that is potentially incomplete. Most disciplines formulate the agent's goal in terms of a scalar signal generated outside the agent's direct control, and thus we place its generation, formally, in the world. In the general case, this signal arrives on every time step and the goal is to maximize its sum. Many other names have been used for reward, such as payoff, gain, utility, and costs. A simpler but still popular notion of goal is as a state of the world to be reached. The goal state formulation is sometimes adequate, but less general than additive rewards. For example, it cannot handle goals of maintenance, or specify how time to goal and uncertainty are traded off. Additive rewards have a long interdisciplinary history. In psychology, reward was used primarily for external objects or events that were pleasing to the animal, and even if that pleasingness was derived from an association of the object with something that was rewarding in a more basic way, a primary reinforcer. Today's usage of reward in operations research, economics, and artificial intelligence is restricted to that more primary signal, and is also more explicitly a received signal rather than being tied to external objects or events. The proposed common model of the internal structure of the agent has four principal components: perception, reactive policy, value function, and transition model, interconnected by a central signal, the subjective state. The perception component processes the stream of observations and actions to produce the subjective state, a summary of the agent-world interaction so far that is useful for selecting action; the reactive policy, for predicting future reward; the value function, and for predicting future subjective states, the transition model. The state is subjective in that it is relative to the agent's observations and actions and may not correspond to the actual internal workings of the world. In deep learning, the subjective state is typically the transient activity of a recurrent artificial neural network. In control theory, the computations of the perception component are often referred to as state identification, or state estimation. In general, the perception component should have a recursive form allowing the subjective state to be computed efficiently from the preceding subjective state, the most recent observation, and the most recent action, without revisiting the lengthy history of prior observations and actions. The perception component is not just about short-term memory, but also about representation. The perception component converts the stream of observation action events into a summary representation that is relevant to the current moment. A dictionary definition of perception: the neurophysiological processes, including memory, by which an organism becomes aware of and interprets external stimuli. The reactive policy component of the common model maps the subjective state to an action. In engineering, it is common to assume that perception is given, not learned, and not even part of the agent. Engineering clearly has the idea of a reactive policy, usually computed or derived analytically. Artificial intelligence systems more often assume that substantial processing is possible before acting. Classical psychology has its stimulus-response associations. In psychology, it is common to view perception as some that supports but precedes action and can studied independently of its effects on particular actions. The value function component of the common model maps the subjective state, or state-action pair, to a scalar assessment of its desirability, operationally defined as the expected cumulative reward that follows it. Value functions have a very broad multidisciplinary history. They were first extensively developed, in optimal control, operations research, and dynamic programming, as cost-to-go functions satisfying Bellman equations and, in continuous time, Hamilton-Jacobi-Bellman equations. In economics, they are called utility functions and appeared initially as inputs to economic calculations capturing consumer preferences. In psychology, they are related to old ideas of secondary reinforcers and to newer ideas of reward prediction. Within reinforcement learning, value functions are used extensively as critical components of the theory and of almost all learning methods. Artificial intelligence and operations research also have a long history of search methods that operate on approximate cost-to-go functions. In neuroscience, the error in the value function, or reward prediction error, has been hypothesized as an interpretation of the phasic signal of the neurotransmitter dopamine. The transition model takes in states and predicts what next states would result if various actions were taken. The transition model could be termed a world model. But this would overstate its role, as much of what constitutes a model of the world is actually in the perception component and its state representations. The transition model is used to simulate the effects of various actions and, with the help of the value function, evaluate the possible outcomes and change the reactive policy to favor actions with predicted good outcomes and disfavor actions with predicted poor outcomes. When this process is done without actually taking the actions, possibly even without visiting the states, then it is appropriate to call it planning, or even reason. Transition models play important roles in many disciplines. In psychology, internal models of the world such as provided by the transition model together with perception have been prominent models of thought. Tolman showed that the results of many rat experiments could be interpreted as the rat forming and using a cognitive map, i.e., transition model, of its world. In neuroscience, the hippocampus is now widely seen as providing such a map, and theorists including Carl Friston and Jeff Hawkins have extensively developed brain theories based on this idea. More recently, in psychology, Daniel Kahneman has proposed the idea of two mental systems, System 1 and System 2. The first three components of the common model of the agent fit squarely in System 1, and model-based prediction and planning are naturally interpreted as important parts of System 2. In control theory and operations research, it has always been common to use transition models of many forms, including differential equation models, difference equations, and Markov models. Models of the world are a common assumption in classical artificial intelligence, such as in single-agent and game tree search. In reinforcement learning, model-based approaches in which the model is learned have long been proposed and are now beginning to be effective in large applications. In modern deep learning, prominent researchers such as Yoshua Bengio, Jan LeCun, and Jürgen Schmidhuber all place predictive models of the world at the center of their theories of the mind. Purely statistical model often provides little insight beyond modeling associations between epiphenomena. The path towards autonomous machine intelligence by Jan LeCun is essentially the same as the intelligent agent framework proposed by Richard Sutton.